because this is going to lead on to the next bit of the tutorial. And what we're going to use is, from the tutorials, it's the MDM2 which contains a set of images. Now, I'm going to ask you to trust it. We're going to do it step by step. You could sort of see earlier I ran this through automatic. So I'm just going to take this through ZIA2. I'm going to run ZIA2 on those images in the cloud. I'm going to hopefully remember all the steps so I can get rolling a decent project. However, we'll see. So, a little bit more information, and this is all in the tutorial directory. There's a Newfoundland 3A complex. And we have images, we have an unmerged file as well that we used earlier. We have a couple of PDB files, we have a PDB file for the search model, we have a sequence, and we have that smart string that we can use. Now, obviously, what you could do, if you were lazy, is run ZIA2 followed by one of the automatic workflows. Take it from there. So, dropping out from there and going back to cloud, you see this automatic sheet is still running. It takes time. Sorry. Lesson 1. Always plug in your network connector if you expect it to connect. Right. Yes. So, can everyone log into CC4 Cloud? CC4 Cloud Remote. Is everyone in CC4 Cloud Remote? Yes? Yeah. If you need help, can you stick your hands up and go on or keep Now, previously ran those automatic jobs, and you can see that they've run, so using cloud, just quickly show that. We have a job. It's run through an automatic processing based upon that unmerged MTZ file. Now, I've just fired this off. I haven't attempted to do anything. It's got to about 30, free of about 30. Right, not great. That's a start. I'm now going to step back and I'm going to go through this from ZIA2 manually. So, back to my projects. I'm going to add a project, and I'm going to call it MDM2 because it's MDM2. That's the tutorial. I'm going to start it manually. Okay, I'm going to add that project. Let's do this. I'm going to import various bits of information from cloud storage. So if I click on that, and I can select the files. I want tutorials, data from images, MDM4, and I'm going to pick up
go a little bit slower.
Okay. I'm going to pick up those files. I want you to get to lunch at a time. So do you see the route through? It's just clicking through tutorials, data from images using the import from client. And I'm just going to select those and upload those. I'm not including images. It won't do anything with the images. Yeah, I don't think. We'll add the images at the next step. So that'll give me a lot of what I need to do. And that, for example, PDF is the tutorial. So that's what we're going to be doing. Now, we should be able to load it and launch it in a separate window so you can see what you're doing. We'll see if I can actually do that. So if I select those, again, it asks me to just confirm that sequence is a protein sequence. So I just upload it. It tells me the files I've selected. We'll upload those to run them and give me the README, which is what I showed earlier, just read that line. And the full example, that's the PDF. It's going to run. And I can open that in the window. And then I might actually be able to read it. So, if you click the button if you load those, everyone loaded those files. Yeah? And then, if you click open in a new window, you can have the tutorial there. So you can read through, you can spot the bits I missed. So you can do it correctly if I do it wrong, okay? So this will just give you more information on what's going on and what we're going to do. Should I deviate from this? I'm wrong, it is right, just so you know. Find the client instance. Okay, I've imported those. I now want to do the data processing. So for that, I'm going to add a job. And it comes up with suggested tasks. And I don't see data processing in there. So, if necessary, I can search. If I have an idea a task is there, I can search for it using the data set, or I can just scan the all tasks and I want. Automatic image processing using ZIA2. So I could run this using my local file system or using cloud storage, which is what you're going to do. The net effect of these is the same. I'll get the same files at the end. If I run it on my local system, it knows which directory I launched it in, it will automatically load the files back up. I'm going to browse again to the same location, and images, and hopefully I get the format correct. And you'll see it's loaded the MDM2 image set, which is a Mars CCP, probably 1 degree oscillation, and there's 60 images. It's a small data set. It's not 1,800 images, it's small. So we can use it in tutorials, good, right? I've got that, everyone got those?
You did the same.
Anyone not got? Anyone got? See, these are, you know, the union of that set should be everyone in the room, or, and so dials can be used on multiple data sets. So I could add another data set. You also see there's a couple of other dials tasks for running serial crystallography data. So you can run single stills or small sweeps. That's in there. I don't think it's an older version of dials. It's not that much mature. The next release, it's a lot better. So there's a new version of CCP4 coming real soon now. So you've uploaded the images.
It's a question, Charles. Question for you.
Question about the image extension. Does it read any
Does it
or
read?
has a specific extension?
Reads a lot of files. It will read many of the old files, but not all. There's some are proprietary and it's a bit difficult. It will read CBS. If you're uploading HDF5s, you will upload the master file. And that gives the information to the rest of the files. So it also probably not read all. If you're doing electron refraction, you may struggle with some of those because again, unofficial file formats, a bit proprietary. But if you contact the guy named David Waterman, he'll work on getting them up. What you probably also want to do is give sensible names so you can track through. If you are doing anomalous data, you will need to give it a heavy atom type. Otherwise, it's merged the field pair together. In this case, we're doing molecular replacement. It's a tutorial. I'm not going to bother. See, there are other advanced options. If you've got small molecule set, dials can be used for small molecules, or CO2 can be used for small molecules. What this does is give us access to a greater number of space groups. We can also run in different modes. If you have XDX installed, so Cloud has XDX installed, CCP4 Cloud doesn't, Lectures Cloud does, you can run CO2 to run XDX. Or you can use dials, symmetry, or you can use aimless. So there's multiples, I'll just use dials. You can set resolution limits, you can force a space group, unit cell, etc. You can change what the cutoffs are, the high resolution set. I think dials uses, not dials, CO2 currently uses 0.16, which is probably an Iowa sigma of about half. That's an idea coming from electron diffraction, the pair ref stuff. Often, I think that's a little bit aggressive. Might want to take that back. But at least initially, you don't lose anything. So, once we've loaded the images, we set anything we want to set.
If I have a many data set, should I load at the same time? I mean, the different wavelengths, or I should be able to distinguish them, or
It'll be multiple experiments. It should be able to.
Okay.
He says, crossing fingers.
Okay.
How would you do it? I've only ever run it in separate and tried merging at the end. I know you can combine multiple different experiments so you keep similar parameters, but I'm less familiar with doing that. Yeah, most of the world is just using single wavelengths. Very little experience. So if I just run that, you'll eventually, as everyone click run. And launch the CO2 job. Yes?
I think so. Some of them are queuing. So.
Yeah, it may take some time. I've got a horrible feeling for some of the lags that we're hitting our machines a bit hard for some other reason. And you'll see, if you click on main log, you will see the standard CO2 output. So it gives information like the number of strong spots found, and eventually information on the possible levy groups, etc. So this is pretty reasonable data, and you find enough spots to index. You know, I might get worried if there were very few spots. I might get worried if the number of spots drops off sharply, but we have a reasonable number of spots across the board. So assuming I've checked and there are no ice rings, I'm reasonably confident. This will take a bit of time to run through, but hopefully not too long. Whilst this is doing its thing, I'm going to, okay, you start seeing the possible indexing solutions. And the indexing solution it's chosen. So, hexagonal. So, it's typical CO2 output. I'm going to briefly divert. You do not need to do this. But I'm hoping to save a bit of time. If I've run in remote mode, I can also run interactive processing using DOE2. You can launch this if you want. It's not part of the tutorial. I just want to show DOE2. And hopefully we'll launch and behave. So DOE2 is a graphical interface for dials. Now the easiest way to run dials is obviously to run CO2 and let it do it, or let your Synchrotron do it. If you have problems, the next step down is to run DOE2. Now, DOE2 is an evolving interface that is tightly integrated with dials, and you'll see a little tree being generated at the side as you step through, and it should, here it will give a list of possible dials. So, again, text is really small. If I import images, you don't need to do this, you won't have images locally. And I find it difficult to read. And if I click run, hopefully we'll load everything, though I miss one of the images out. And you get, it will load up the images and you get a picture of the image there. And you'll see Luis, who designs this, likes it in that view. I hate it in that view. I much prefer inverted, I say grayscale too. That looks nicer to me. So those are the images I tell you to always look at. If I click, that's running dials import. If I look at the log file, you can see it imported 60 images in one sweep. It's good. If I look at the report information, there's no report information at the moment. Fair enough. Now, it tries to lead you through, so dials, you run through, dials import, dials find spots, etc. So if I find the spots on this, just run, I can change various parameters. The background, Sigma background, etc. It used to be a problem that Your images would have a lot of artifacts on there. You might want to reduce the number of spots you find, so you might want to change the thresholds for spot finding routines. That's something we're having to do much less often now. So I'm just going to run for the sake of, and just do a find spots. Now this is running on my local machine. I'm just finding the spots, so if you check the log file, you can see it's found the same number of spots as find. You'll see there's a little bit more information, experimental information coming up. So if I click a report, I see more information. And as I step through, I get more and more information built up. ZIA2 will do this automatically. I'm not going to take this any further, because there's a nice tutorial online about running DOE2 for dials. I don't want to take any more of your time, although I want to find it. I want to quickly fire up the reciprocal lattice view, which is the thing I showed you earlier. And it'll fire up. And that's the reciprocal lattice view, and you can see that's our spots. And this, if you went through later, through the process, you'd find more information on there, your indexed and unindex spots. Now, that is the correct spindle. You see, difficult to line. I should be able to line this and get nice straight lines. Fantastic, look at that. Straight lines, looks good. I see a little bit of noise along the rotation axis, but your data processing program will ignore those as far as indexing is concerned. Now, I quickly wanted to just show invert spindle, and you'll see. Hopefully you'll see that I've now got those curves I showed in the talk. It's difficult to get an angle, but you see it's now a curve, it's not a straight line. So this is a useful tool for just checking pathologies. And I would suggest that if you are manually processing, you do look at this and give it a go. As I said, there's another one called RS Mapper to do additional. So if ZIA2 fails, my next step down would be to run DOE2 and just step through the process and try to make the way through. Now, that's run local. Because there's a known directory, if I run through to the end, the results would have been loaded back into the cloud. As I've just broken the connection, I'll probably get a message that connection's broken. And I should do. If I relaunch that and continue, it should be in the same directory. Okay, back to ZIA2. ZIA2 is completed, and it's given me 3 files. So it's given me a merged MTZ file, and as when I imported, you can see the information for that, including the estimated resolution, the unit cell, the guess space group, the wavelength, what's in the MTZ file, etc. And various bits of analysis are in there as well. So the Wilson plot, some L-test, always worth checking eventually. The L-test. Now, you check how this looks, and this is an untwinned example, it's good data. Also got an unmerged scale file. and you'll see it's run the same test as when I uploaded our merge file. And it contains information on the possible space group settings. So which axes are there, which axes aren't there. And if you look at this table, you'll see we've got the likelihood of particular symmetry, and they're all very strong. So the first one is comparing a reflection to its Friedel mate. So, and that's basically our null hypothesis, that that's a symmetry we know we've got. And then we compare the other symmetry, the other rotation axis to that, and you'll see we have very strong signal. It's a very good data set. We then have the scores for the Lowry group. This is a 6-fold, so we've got P6 MNN. With a very strong confidence that it's that. We then look at possible systematic absences to what's possible space group it is. Looking at that, we have 2 possible space groups come up for this. So our systematic absences has given us a possibility of 6-1, 6-5. So we're going to have to carry that information forward. Data processing will have selected one of them. We have to remember it can be either of them as we go forward. We will not know until at least we completed molecular replacement. Okay. That's a summary of information taken back into C64 Cloud. I can have a look at, okay, finally there's another unmerged then. This is unmerged, unscaled, so it's the most generic information we've got back. But again, it all looks very strong. Field Gulf Group, look at the CO2 report. You can see basically table 1, the CC1/2 information. And you'll see it's very good correlation and even pretty decent coming out of shell. Our multiplicity is good. We have good completeness. We're probably missing a bit towards the edge. Our merge is beginning to get a bit high in the outer shell. Okay, I might want to check that. If I then click on another button, the dataset native, people click on that. So this gives more information from the ZO2 report. Previous one is just the summary of the table 1 information. This gives a bit more. This is always worth checking. So it breaks out low resolution, high resolution, etc. You can roll down and have a look at statistics. And we'll see our completeness is pretty. Yes. Completeness is good. I over sig I is good. Our merge, okay. Beginning to be a bit of concern in the outer shell, but still correlation coefficient is great. Okay, I play continue. Okay, Z2 runs X triage. X triage is fired up a warning. There are a large number of outliers in the data. Okay, when I looked at the summary, it looked great. However, this gives me a bit more of a concern. So, I click on that, I get a bit more information, which outliers there are. And there are a lot of them. Okay, that's a concern. Possible outliers are an issue. So, I want to click out and have a look at various plots that are presented. Now, by resolution, we scroll down, I can look at the CC1/2 by resolution. And what we're seeing here is something that's fairly common. The CC1/2 is going up at the end.
Can you explain what CC1/2?
Okay, CC1/2, we randomly split the data into 2 halves, and then we compare the same reflection in each half. Now, if the data is good, we should have 100% correlation between the two sets. If the data is totally uncorrelated, anti-correlated, it'd be -1. If it's noise, it would be 0. So I have a sigma of about 1, it would be about 0.3. Now, what's my resolution? It's a horrible question because it depends. What may be good at one part of your pipeline may not be good at another part. Maximum likelihood programs are very good at dealing with noise, so they can take into account poor data and downweight it, but not everything, particularly in experimental phasing, is maximum likelihood. Probably you want to cut back reasonably conservatory, a reasonable amount when going through molecular replacement, model building, etc. And you can add the data back in at the end. Now, you can use something like the pair ref procedure to add it back in, and as long as it has the same statistics as good data, it should improve your maps. And at the end of the day, a good map is what we want. But I'm looking at this, and although it's saying CC1/2 is pretty high in the outer shell, it's actually dropped beforehand, so it tells me I'm probably going to too high resolution. Now, that can be because I've got few spots, so my statistics are not very good. I've integrated out to the corners of a square detector until these guys make round detectors. I'm gonna have to do that. So it could be that. However, my completeness is pretty good, so it's maybe not that, and it might be it's just noise out there, and random noise can have quite a good correlation. So if you've got zeros in both counts, it's 100% correlation. So. Okay, that's one. My resolution's a bit, looks like it might be a bit high. And yeah, I1 sigma is quite sensitive to that, and that's skyrocketing, so yeah, probably my resolution's a bit high, and yeah, my Wilson plot is diverging as well. So there are warnings. So I probably want to cut back resolution, fine. Other places you should look. The analysis versus batch is really useful information, particularly if there might be radiation damage. So if you use aimless, it gives slightly different statistics. So this gives R merge and the scale. I think aimless gives the B factor weighting as well. So as well as trying to scale all the reflections to the strongest, all the data to the strongest data, it tries to upweight the high resolution data to the early data. Now, R merge is starting to climb quite significantly here, which makes me a little nervous. The scaling is also having to work quite a bit higher on the latent data sets. So it's a bit of concern that I'm getting radiation damage in there. I might want to consider cutting back. I should look and check what my completeness looks like. So I don't want to cut out data if I'm losing too much information. So, no, we also see that on sigmas dropping. Completeness, I'm pretty complete there as well. So, I think what this is telling me is I want to discard some of the data at the end, and I want to cut back resolution. We also have various other plots in there. So we have the eccentric, eccentric L-test. So we have the L-test information again. This is not twinned, it's fine. We have distribution of spots on the data, on the panel, and the distribution of our recorded intensities as well. So lots of information that we can look at. And if you look at the Dials report, there's actually more information in there, shapes, rods, and so on. It's all worth looking at and checking, particularly if something fails later on. So having looked at that, I think I want to rescale the data using Aimless. I don't need to reprocess, I'm not changing space group. I'm getting rid of reflections at the end. So there's a little note. Dials is a 3D program that uses rolling scaling. If I discard reflections in the middle, I probably want to reprocess from the beginning, starting there, because bad images in the middle is set the entire side. As this is at the end, I probably don't need to do that. So I want to, as I'm not changing space group, I can use scale merged, unmerged, and I want to tell it to just run 1 to 50. I'm going to keep the previous solution from merging. I am, however, going to change the high resolution limit. I should have paid attention. I'm going to take 155. Okay. It's just a guess because I didn't pay enough attention to what the thoughts were. The text will probably tell you something different. I'm just cutting back to get rid of that. Once I put those in, I want to click this back and I'm not scaling. My data's already scaled. I don't want to scale again, so I'm just merging the data. If I'd used, there's another unmerged data set there. If I'd used that, I would have to do scale in this game. And I just click run.
Can you show that again?
Okay,
Just the input, what you put in.
yeah, go back to the input, right? So what we've got is the data we took, which was just the default, which is an unmerged scale, number 2. I have decided, based upon looking at the R-merge versus batch, to get rid of the last 10 images. That doesn't affect my completeness, but yeah.
Okay, so when we want to change the space group, how we can change the space group for the
So you can change it using pointless. So you just change the space group. As long as we're running the same Lavi group, it should be fine. I'm actually going to, there's another example I want to show that there's a twin data set and that comes up in that. So I'll show that later. So, and I'm not changing the symmetry information, so I'm just taking everything and running through. So, and the output. If I looked at the log, I can see the output of various files. There's some information in here that's not elsewhere. So it's, if you know what you're looking for, it's worth clicking through after you've read the documentation and just checking in detail, particularly if something's going on. However, we can just look at the report, and we want to look at the scaling and merging information. We've reduced the symmetry, well, we've reduced the resolution, so we're obviously going to have better completeness, better, well, we've reduced the number of images, so our multiplicity's dropped. We're going to have a better eye on SIG-I because, well, we have a more realistic eye of SIG-I because because we've clicked back to earlier the data set. We can check, because we cut it back, it's pretty well to where I set the data in all directions. So Aimless is giving various suggestions for the resolution. So CC1/2 resolution would be 1.55 or 1.58, and it's given other ones using the Minax I/CD. These are suggestions we take forward. Now, if I look at the information of this, the if I now look back at the Wilson plot, you'll see, okay, it's still a bit noisy at the end, but generally looks better. If I look at the eccentric moment, the second moment, again, it jumps a bit at the end. It jumps quite a lot, but it generally looks better. I could, if things go wrong, cut this back further. But as I said, maximum likelihood programs probably not going to be an issue. So what I've done, just adjusted my merged data for using further down the line, which are tutorials on library replacement using Aimless. There is something else I should show, and at this point I hope it works. The best way to check for ice rings is to use your eyes. Various programs also check for ice rings using either deviations of intensities from expected or something similar. Auspex uses IOPON-SIG-ion resolution values. It takes a long time. And I don't know if it works, but I'll give it a go. Auspex checks for ice rings. So I'm just flying that through to check if there are ice rings in the data. Another test. Right. There we have the IOPON-SIG-F data, and we'd be looking in the greyed areas to see if it deviated markedly. If it did deviate markedly, to be a sign of ice rings and a problem. You know, we've got two distinct bands there. Should I be worried? Why have I got two distinct bands? Anyone got a guess? This is Fs to our amplitudes. They are our centric and eccentric reflections, so they have different distributions. So I have, I'll get this wrong, I think it's the top one's the eccentric, and the bottom one's the eccentric. The limit of them is different, the distributions are different, so you will typically see two bands. Now, hopefully you don't see anything horrible like steps that might suggest something's going wrong with your data processing. If you see dips, as I said, in the grey areas, you may have ice rings. Again, it's a way of just checking your data. Now, I processed this, as I said, this was nice and quick. I would then do something you're not going to do. I'm going to try and remember how to do this. Change teamwork and sharing. I'm going to add you're on MK65, aren't you?
Yeah.
You don't need to do this, certainly not with Roland. get really sick of the time if he gets 30 invites to join a tutorial project.
Okay, can you share with another account, so I have a test account,
Okay, what's your test account, Ron?
so it's JOEBLOE,
Oh, do you want to type that?
JOE,
Sorry, just moved my laptop. Escape. You are JOE
ELOE.
Joe Blow.
Oblong.
Right. Yeah, share group. Okay. So that's a useful tool in cloud. When you're using our cloud, you can share it with other cloud users. Useful if you need to call an expert like onto your Bevadev because you've got twinning, it's horrible. Useful for sharing with your colleagues who might want to work on the same data. And useful for sharing with your supervisors so they can check what you're doing. Right, that's me finished with this one. I'm going to run another one whilst you get your lunch to set up for a twinning tutorial. And that will hopefully partially answer the question from Guy in the back. Are there any questions on that? As I said, it's limited. You can upload data, you can upload data using Globus. Truth, I don't think you're going to gain that much at the moment over what you get from the Synchrotron, but it is there. Any questions? No questions? Shall I say I don't let you go for lunch unless there's 5 questions?
Too early.
Is it too early? Oh my God, it is. Wow. Okay, even better. Ron's going to do something now. You have to excuse me, it's already been a long day. There's me looking forward to lunch.
Okay, so before we do lunch, I'll show you a little bit about the next step. So Charles has shown you how to do the image processing, how to process your diffraction data into a merged data set that we can then use to go on and solve our structure with. So I'm going to show you how to do the next stage, which is basically to get the phase information through molecular replacement. And what I'll do is I will do a short presentation now just to point out a few things you need to be aware of. And after lunch, we'll continue on with the demonstration that Charles has shown you, has started. And what I'll do, since we introduced you to Dexterous Cloud earlier, I'm going to work within Dexterous Cloud to show you how it works. You can follow outside of the Dexterous Cloud or inside, whichever you prefer. But it'll be the same either way. I'll be using CCP4 Cloud within Dexterous Cloud. And the big advantage of Dexterous Cloud is going to be that you'll be able to connect to the synchrotron beam lines directly to the diffraction data that you've collected and pull it into the cloud, and then you'll be able to process it directly with CCP4 from within. Yeah. Can you get in? Okay. All right, yeah.
They have started it, but I don't know if that will work.
Okay, I'll do it. All right, so I'll close that and I'll go back to my Dexterous Cloud,
You have to do it at home,
the home area.
so you'd be there.
Yeah.
For everybody like that.
Okay, so if you want to follow me in Dexterous Cloud, go to the home area like we have here, that we also made earlier. advantage Dexter's Cloud has is that you don't have to have CCP4 installed on your own machine. Once you've logged in through this, you get all the CCP4 programs installed within it. All good? Alright. So if you can all see this view, and you've all created this instance of this is a virtual machine that we're going to run CCP4 within. We can click open to start that up. So we click open. I'll take a few seconds. And you should get what looks like a desktop in your browser. Can you all see this? Anyone not at this yet? Give it a few seconds. Yeah. So essentially what this is it's just like a desktop operating system desktop. And in this case it's Ubuntu Linux. If you've not used Linux before, I'll go through it slowly. But it works just the same way if it was installed on your own machine. So to start CCP4 Cloud in here, what we need to do is open a terminal. So we click, because you don't have the icons, do you? You don't have the CCP4 icons.
I'm not sure.
I don't think they appear. So yeah, we need to start a terminal so we can run it. You click these 9 dots in the bottom left and bring up this menu. You'll see the terminal in the middle somewhere. Okay, so that's clicking on the 9 dots, and then you get this list of applications, and we want terminal. So I click on that, and that will open up a terminal like this with a command prompt. And the only thing we need to do in here is we just type CCP4 Cloud -remote, like that. And that will start up the CCP4 Cloud host. Now we will remote, so we can connect the chart to your project that we've already started. Okay, when you type that in, just press enter. All right, everybody at that point? So I'll press enter, and that should load up a browser, and like before, it will ask us to log in to the session, to our account. And this is my account. So we'll log in. So I have no projects here, but what you should see is the projects you've already created today. So you see the MDM2 project in the same way. So this is the exact same cloud interface that you've used before. We're just running it inside Dexter's Cloud. All right. So, what shall I do first? Okay, so first thing I'll do is I'll join the project. You don't have to do this, but Charles shared the project with me, so I'm going to join Charles' project. I click on join, and then here it tells me that Chucky B or Charles has shared a project with me, and I just click join. And we'll see. I've joined the project. And I can double click in. And I can see what Charles has done already. So now I'm a member of this project as well, and I can continue on. Okay. So I'll continue this on after lunch, but before we do that, I want to show you some slides. Now there are several molecular replacement tutorials within CCP4 Cloud. So what I'm going to do is I'm going to go back to the projects menu, and I'm going to add a new project, and you can do this as well if you want. I'll add a new project. Oh, the project there. Add a project. Can I create project in this folder? Oh, this is because it's Chucky B's projects. So I need to go back to my projects. Okay, so this is where you will be. So I'm going to add a project in here, and I'm going to call it MR example 1. Okay? We're just going to call it molecular replacement. Example 1. So this will be our molecular replacement example for our first molecular replacement example. So I'll add that project. And then like we did before, I'm going to take files from the cloud storage, import from the cloud. And then I'll select files. And I'll go to tutorials, data again. And then this time to from phasing. To phasing. This one in the middle. Okay, and that gives a big list of folders of different types of phasing examples. And there are three that we're kind of interested in today are these three here, 1, 2, 3, MR1, 2, 3, which are three different examples of the kind of molecular replacement scenarios you're likely to encounter when solving a structure. And the first one is a very simple example, but it's the most typical, the most common that you'll encounter. So I click on that one. And then like before, I've got a set of files, and I'm going to highlight them with the shift key. So I press shift and the first and last file, and then I can select those files. Is everybody up to that point? Yeah. Okay. So I select those files. And it's asking me, it's spotted that I've uploaded a FASTA sequence file, and it wants to know, is that protein or DNA or RNA? So if it was DNA or RNA, I could tell it here, but in this case it is protein. So it's the protein sequence. So I click apply and upload, and then finish import. And what we've selected is a sequence file, merged MTZ file, so that's our reflection data, and there's also a PDF document in there as well. The thing I'm interested in hasn't appeared. I'm interested in the PDF that's not appeared there. Just do it again. Why isn't that appearing? Does anyone get the PDF file? Can you see in the tab across the top? Oh, there it is, I got it now. All right. Can everyone see this? This PDF document, MR example in the tabs? You have that? All right, so that's what I'm interested in. So I'm gonna open that in a new window. So if you click on that tab, you see this open a new window option here. I'm going to click on that. And this is basically a few slides of introduction and a tutorial at the end that you can do yourselves. Okay. So can I get this to go full screen? Presentation. All right. Okay. So this is a simple example demonstrating the typical molecular replacement scenario where you have a simple single molecule in the asymmetric unit. You're going to do a prediction using AlphaFold, and then we're going to prepare that model for molecular replacement. And we use Phaser to do the molecular replacement. And then afterwards we'll do a little bit of refinement to correct the model. But I'm going to start with some slides that just talk about some of the typical problems with molecular replacement and things to be aware of. So this is the fundamental equation that we're trying to solve in the experiment. So this, you'll see this before in Charles' talk, but this is the solution to the density equation. So what this tells you is that the density at any point x, y, and z, three-dimensional point in our map, is given by this Fourier sum, which basically has two key terms in it. One is the amplitude term, which is given to us by the fraction intensities that gives us the amplitude measurements. And the other term is this phase term here, which we don't get from the experiment. We have to get it by other means. And nowadays, all of the time nearly, we do this through molecular replacement. So we take a model for our target structure and we use molecular replacement to place it in the unit cell of our unknown structure. And that gives us the phase information. And the reason why this works so easily now is because we have AlphaFold. And AlphaFold predicts our structures very, very accurately. And it will give us the phase information once we place it correctly. And the process of molecular replacement is basically rotating and translating that model into a unit cell of the target until we find a point where it agrees best with our experimental data. And that's the whole process. So, there are some issues though that you can encounter with it. This is sort of 5 of the most common scenarios that you'll encounter when you're doing this, when you're doing molecular replacement. The first one is a simple scenario where you have a single molecule in the asymmetric unit and you get a very good prediction for it. And it's pretty straightforward to solve. Any molecular replacement program will solve it for you. But then you can get more complicated scenarios, like where you may have a multimeric content in the asymmetric unit, or you have several molecules present in the asymmetric unit, and you're looking for more than one. And these cases can be a bit more tricky because essentially it's a signal to noise problem. You have the signal coming from your model, and the noise is what you're trying to find that signal against. And the bigger your model is, the better. So you can try things like produce multimeric forms of your target structure, and that will help with the placement of the model. Another typical scenario is where your AlphaFold prediction has a different conformation in the relative orientation of the domains within the model compared to your crystal structure. So if that happens, then the model itself won't make a good model in molecular replacement. And what you have to do is you have to break your model up into those domains and search for them separately. So that's another common scenario. Other things that can happen are where you have problematic data. You may have like twinning or pseudo-translation, and they can convolute the process. Most of the time what they do is they hide the true space group. So you may have to consider trying other space groups when you encounter things like twinning. Another thing that can happen as well is you can have contamination. So Charles mentioned a program called SIMBAD earlier, which is designed to test for contaminants. And there are about 60 or 70 proteins which regularly contaminate crystallization. Things like that come from E. coli, they can get into your drop and they can crystallize instead of what you wanted to. So if you're having trouble solving your structure, always consider the fact that you might have a contaminant and try programs like SIMBAD. And then another scenario is where the predictions are poor and they don't work. And this can sometimes happen when you're dealing with like a structure that maybe consists of a lot of helices. So you have a helical bundle, and often AlphaFold can have trouble predicting the correct orientation of those helices relative to each other. So in that case, there are programs in CCP4 that can help. There's a program called Archimboldo which will take standard helices and search for them, and it can give you enough of a signal in a molecular replacement search in order for you to complete the structure. So if you do get into the scenario where you can't solve it, you can try programs like Archimboldo, and they might solve it for you. Okay, so they're the most typical scenarios, and I'll go through how to do molecular replacement in CCP4. So CCP4 Cloud specifically. So the first thing we always do is when we come from the data reduction and we have a merged MTZ or data file, reflection file, is we then want to find out or guess, make an estimate of how many molecules we have in the asymmetric unit. And that's what this task is for, contents in the asymmetric unit, and you see it with this logo in the cloud, CCP4 cloud. And what this does is it takes our unit cell, it knows the volume of our unit cell, and it takes our sequence, so it knows the molecular weight of our structure, and it tries to figure out how many times that molecular weight will fit inside the unit cell. And typically, crystals of macromolecular structures like proteins and DNA and RNA, they consist of about 50% solvent in the unit cell. So it sort of traditionally tries to get a value of about 40 or 50% solvent and then considers the rest to be protein or whatever macromolecule we have. So that's what this is working out. And nowadays we have a new way of doing it where we've used the AI, trained AI, an AI model on all of the existing structures in the PDB. And that can give a slightly better estimate of, particularly when you've got higher loads of what you have in your crystal structure. So we'll show you that in the demo. The other thing that this step does is it sets up your initial, what's called a revision in CCP4 Cloud. So a revision is everything we know about the crystal at that point. So up to this point, you know everything about the reflection data set, you know about the volume of your unit cell and its parameters and the possible space group. And after this point, we know how many molecules are likely to be in that crystal. And when we go on, we start to add phases and models to it. And so the revision gets updated as we move through the structure solution process. Okay, so if you're wanting to generate models, there are lots of ways of doing it. Probably the best way is to use the AlphaFold 3 server, which allows you to do DNA and RNA and protein complexes, and even allows you to predict where ligands are. So that's a pretty good way of doing it. There's other things like fold sequence, which is from Meta. Tends not to be as accurate as AlphaFold, but it can be useful sometimes. There's also Rosetta Fold. If you're looking for multimers, there's online servers that specialize in making multimers like Unifold, which is particularly good at making symmetric multimeric folds. There are also various databases available. So there's the AlphaFold protein structure database, which has about 250 million predictions in it. And then there's a group that created, they didn't include virus structures in this database because they didn't want to. They thought it would be ethically unsound to do, but there's another group who created what's called the Big Friendly Virus Database, which includes the virus structures generated using AlphaFold. And then there's also something called the ESM Metagenomic Atlas, which contains a whole load of metagenomic sequence predictions done with ESM-Fold. It has about 700 million predictions in there. But within CCP4, there's two main ways of getting predicted models. There's the structure prediction task, which runs Colab fold or essentially AlphaFold underneath. And then there's also a way of searching the AlphaFold database and the PDB database for models, and a program called MRParse, and that will give you a sort of tabulated view of all the hits that match your sequence. So it does a sequence-based search. So as I said, AlphaFold 3 tends to be the best. If you're struggling with the other ways, then go to the AlphaFold 3 server and use that to do a prediction. And as particularly with multimeric structures, if you're trying to predict a multimer, a heterogeneous multimer is a very useful and the most accurate way of generating those kind of models. Okay, so we're nearly at lunch. I'll finish these slides and then we can go for lunch. Just to say about predicted models then. So when you predict a protein, you see a representation something like this. So what this shows you, essentially the colors show you the confidence that AlphaFold has in those particular residues. And blue corresponds to high confidence, which is high numbers like greater than 70. So it runs from 1 to 100 in terms of values, but values that are greater than 70 will be colored blue. And those residues are where AlphaFold is confident the prediction for those residues is correct. Where they're yellow and orange means it's not so confident. It means those residues probably aren't correct. And what this means for our molecular replacement or our crystal structure is that if we're going to use this as a model, the chances are these orange and yellow parts, they're not going to be present in the crystal structure. So before we go to do molecular replacement, we need to remove these parts in order to help molecular replacement work. And the other thing is Phaser molecular replacement program uses beat factor information to help guide where to position the model. And these PLDDT scores, which are the confidence scores that we're seeing here, are stored in the beat factor column of a PDB or a ZIP file. So we can't just give that straight to Phaser. What we have to do is convert those PLDDT estimates to beat factor estimates and then give it to Phaser. So we have programs that will do all this automatically for you, but that's what they'll do underneath. They'll do this conversion before we give the model to Phaser. So it's important that you do this pre-processing step before you do molecular replacement. One other thing that is done by these automatic pre-processing programs is they also will look at the domain layout within a predicted model. So if you've got a larger model that may consist of more than one domain, you can ask these programs to split those domains apart. So like I said, sometimes you need to break the models up in order for molecular replacement to work. And these programs can automatically identify where these domains are. You just tell them how many there are, and we'll break them apart. And the particular program I'm going to show you is called Slice and Dice, actually. And we'll see that in the demo. And that will do all this pre-processing for us. A couple of final things. So in CCP4 we have two main programs for doing molecular replacement. There's MolRep and Phaser. Both of them are pretty good with predicted models. Phaser tends to be more useful when you're dealing in more tricky cases where you have, perhaps you're looking for many copies in the asymmetric unit. Phaser is better able to pick out those solutions because it basically accounts for the errors that are in your model and in your data, whereas MolRep doesn't do that, but Phaser does. So Phaser can be a bit more useful in difficult scenarios. Important things about when you're running these programs, basically within the cloud, everything gets loaded by default as you go along, so you don't have to change much. So it's better to let these programs make their own decisions, but sometimes you may have to, like in some scenarios, you may have trouble finding each copy of your molecule, so you may have to look for one by one and refine between each molecular replacement step. But by and large, just let them run with default options. Then how do you know if your molecular replacement has worked? With these programs, they give very clear indications in the scoring that they provide. So Phaser has this log likelihood gain score, which basically is an indication of how good the best placed position for the model is against the background of incorrect places for the model. And what you're looking for with that is you're looking for a value of 60 or more for each copy of the model you place. So if you see your LLG score jump by 60, then you know it's correct. The other thing to look at is the translation function z-score, this TFZ score. And if that is better than 8, that's a clear indication that the solution is correct. And that's a pair copy score. So for each copy of your model that you placed, you expect to see a TFZ value of 8 or more. MolRep is similar, it has z-scores as well. And again, you're looking for values of about 8 with the z-score. But the key thing as well is that you have what you see in these plots on the left-hand side is is that you have a standout peak value compared to the background. So a very clear indication that the solution is correct is that you'll have one or a few high scoring peaks compared to everything else. And if you just see one value, then that's even better. That means there's only one clear solution. After molecular replacement, you can do a bit of refinement. So often you see something like this if you look at the map after you've done molecular replacement. So here, Phaser has given us a good score, so it's given us a log likelihood gain, an LLG of 102, and a TSZ value of 8.9. So if you remember, I said LLG better than 60 and TSZ better than 8. So that would say that that's a correct solution. But if you look at the map, it looks terrible. And that's often the case after molecular replacement, because the model, although it's correctly placed, it's not yet giving us good phases because we need to refine it. And if the phases are good, we'll see a much better map. So we typically run what's called jelly body refinement after molecular replacement, and we do 100 cycles of that. And I'll show you this in the demo. But when you do many cycles of this jelly body option, which allows essentially the atoms to move a greater distance over time than regular restrained refinement will, and enables a molecular replacement solution to move into a better position, you'll see something like this where the map is improved greatly, and we start to see green density, which is the difference map, which is the difference between the experimental data and the model. So something is missing in the model if we see difference map density. Like here, for example, we can see some water molecules here. This is another case. Phaser solution here on the left, and then after refinement we see a lot more detail in the difference map. So along the top, up here, we can see green density corresponding to parts of the model that need to be built, that are in the experimental data but not in the model. And the reason we do lots of cycles is because it can take many cycles of this jelly body refinement in order to get them to improve the model and start to get it into the right place. So this shows you, if you just did 10 cycles, our R factors, which is a measure of the difference between the model and the data, are still quite high. They're still up in the 40s. But if we do 100 cycles, we can see that over those 100 cycles, the R factors start to drop significantly. And now they're down into the low to mid 30s. And if we look at the density at that point, we start to see much more improved density. And we can start to see things like here, we can see a ligand has appeared. So it's always good to do many cycles of jelly body refinement after molecular replacement. And this is just another example where you can see the density. If you look in Cooch, you can see that, you know, there's obviously this piece of the model needs to be moved into this density where it is slightly shifted from what the model is. And that's always a clear indication that the molecular replacement solution is correct. Okay. All right, so that's the end of the slides for now. So I think we'll break for lunch. And then afterwards, I'll take you through how to do molecular replacement in the project we're working on. Any questions before lunch? Any questions on any of that? Okay. We'll go for lunch then. I think lunch is upstairs on the 3rd floor.